Welcome back to Tech Talk, where we break down complex tech concepts into bite-sized pieces. Today, we're diving into the fascinating world of distributed systems, focusing on consensus and coordination, two pillars that keep our digital world running smoothly. Whether you're a seasoned developer or just curious about how things work behind the scenes, this episode is for you. So grab your headphones and let's get started. Let's kick things off with a fundamental concept, heartbeats. In distributed systems, nodes, think of them as individual servers, periodically send out heartbeats to check if their peers are still alive. If a node stops sending these signals for a duration longer than a predefined session timeout, the system declares that session dead. This is crucial because it helps maintain the overall health of the system. Now, what happens to the locks held by a session that's timed out? Well, Zookeeper, a popular coordination service, can automatically release these locks. This feature is particularly useful for managing ephemeral nodes, temporary data structures that only exist while the session is active. But Zookeeper isn't just about keeping tabs on sessions. It also allows clients to watch for changes in the cluster. For example, if a new client joins or an existing one fails, clients can subscribe to notifications, eliminating the need for constant polling. This is a game changer for efficiency and responsiveness in distributed systems. Now, let's talk about one of the standout features of Zookeeper, its ability to perform linearizable atomic operations. These operations require consensus among nodes, which is essential for tasks like leader election. Imagine you have multiple instances of a service, and you need to designate one as the leader. If that leader fails, another instance must seamlessly take over. This is vital, not just for databases, but also for job schedulers and similar stateful systems. Another scenario where Zookeeper shines is when you have partitioned resources, like databases or message streams. As new nodes join the cluster, some partitions need to be reassigned to balance the load. If a node fails, others must take over its responsibilities. Zookeeper's combination of atomic operations, ephemeral nodes, and notifications allows for automatic recovery from faults, without requiring human intervention. While tools like Apache Curator provide higher-level abstractions for working with Zookeeper, implementing consensus algorithms from scratch is notoriously difficult and often leads to failure. That's why leveraging established tools like Zookeeper is a smart move. So how does Zookeeper manage to coordinate so many nodes efficiently? Instead of performing majority votes across thousands of nodes, which would be inefficient, it operates on a fixed number of nodes, typically 3 to 5. This allows it to handle consensus while supporting a potentially large number of clients. It's like outsourcing the heavy lifting of coordination to a dedicated service. But what kind of data does Zookeeper manage? It usually deals with slow-changing data, like which node is the leader for a specific partition. This data doesn't change rapidly, unlike the runtime state of applications, which can fluctuate thousands of times per second. For that, other tools like Apache Bookkeeper are more suitable. Now, let's touch on service discovery. Zookeeper, along with other tools like etcd and Console, helps services find each other in dynamic environments, such as cloud data centers where virtual machines come and go. When services start up, they register their network endpoints in a service registry, allowing others to discover them easily. However, the necessity of consensus in service discovery is debatable. Traditional DNS systems, for instance, don't require consensus and rely on caching for performance. While service discovery doesn't need to be linearizable, leader election certainly does. If your consensus system knows who the leader is, it can facilitate service discovery by providing that information to other services. Let's dive deeper into the concept of membership services. These services help determine which nodes are alive and which should be considered dead. This is crucial because due to network delays, it's often impossible to reliably detect node failures. By coupling failure detection with consensus, nodes can agree on the current membership of the cluster. But what happens when nodes have differing opinions on who is alive? For example, if one node thinks another is down while it's actually functioning, it can lead to confusion. This is where consensus becomes vital for establishing a reliable membership view. Throughout this discussion, we've explored consistency and consensus from various angles. One key concept is linearizability, which makes replicated data appear as if there's only a single copy. While this model is easy to understand, it can be slow, especially in environments with significant network delays. We also touched on causality, which orders events based on cause and effect. Unlike linearizability, causality allows for some concurrent operations, creating a more flexible consistency model. However, certain scenarios, like ensuring unique usernames, require stronger guarantees, which brings us back to consensus. Speaking of consensus, let's break it down further. Consensus ensures that nodes agree on decisions that are irrevocable. This concept applies to various problems, such as deciding whether to commit a distributed transaction or determining the order of message delivery in a messaging system. In a single leader database, decision-making power is centralized in the leader, allowing for linearizable operations and uniqueness constraints. But what happens if that leader becomes unreachable? There are three main approaches to handle this situation. You can wait for recovery, accept that the system will be blocked until the leader recovers. This doesn't solve the consensus issue, as it can lead to indefinite blocking. Alternatively, there's manual failover, where humans intervene to choose a new leader, but this process is slower than automated solutions. The most efficient and reliable method is automatic leader election, using a consensus algorithm to choose a new leader, especially in adverse network conditions. It's important to note that even with a leader in place, consensus is still required for maintaining leadership and handling changes. So while having a leader simplifies some aspects, it doesn't eliminate the need for consensus entirely. In summary, tools like Zookeeper provide essential services for consensus, failure detection, and membership management. While using these tools can be complex, they are far more reliable than attempting to build your own solutions from scratch. If you're tackling tasks that require fault-tolerant consensus, leveraging established tools like Zookeeper is the way to go. As we wrap up today's episode, it's clear that understanding consensus and coordination is vital for building reliable distributed systems. We've touched on a lot of concepts, from heartbeats and leader elections to service discovery and membership services. If you're interested in diving deeper into these topics, there's a wealth of research and resources available. Thanks for joining us on this journey through the world of distributed systems. If you enjoyed this episode, don't forget to subscribe and leave us a review. Until next time, keep exploring the tech that shapes our world.